In this slidecast, we'll talk about recursion. The objectives are to learn how to think recursively, how to trace a recursive function, how to write recursive algorithms and functions for searching vectors, how to use recursion to solve the Towers of Hanoi problem, how to use recursion to process two-dimensional images, and how to apply backtracking to solve search problems, such as finding a path through a maze. The programming lab you'll do for this chapter will be a maze problem. Recursion can solve many programming problems that are difficult to conceptualize and solve linearly. In the fields of artificial intelligence, recursion is often used to write programs that exhibit intelligent behavior, such as playing games of chess, proving mathematical theorems, recognizing patterns, and so on. Now, recursive algorithms can compute factorials, compute the greatest common divisor, process data structures. The data structures that we are learning about this semester are all efficiently searched and processed using recursion, and we'll see examples of this throughout the semester. We can search efficiently using a binary search and find a path through a maze and many more. Let's talk about how to think recursively. Now, recursion is a problem-solving approach that can be used to generate simple solutions to certain kinds of problems that are difficult to solve by other means. Recursion reduces a problem into one or more simpler versions of itself. Here's a recursive algorithm to process a nested figures. If there's one figure in the nest, then do whatever's required to the figure. Else do what's required to the outer figure and then process the nest of figures inside the outer figure in the same way. Now consider searching for a target value in a vector. Assume the vector elements are sorted in increasing order. We can compare the target to the middle element. If the middle element doesn't match the target, then we search either the elements before the middle element or after the middle element, depending on how that middle element compared to our target. And so instead of searching through n elements, we search n over 2 elements. At each step, we can reduce our search size in half. Here's a recursive algorithm to search a vector. Okay, so here's some pseudocode of what we just described. If the vector is empty, then we return -1 as the search result. That implies not found. Else, if the middle element matches the target element, then we return the subscript of the middle element as the result, and we're finished. Now, if the target is less than the middle element, then we recursively search the vector elements preceding the middle element, and we return that result. Else, we recursively search the vector elements following the middle element, and return that result. So here in these final two choices, we're eliminating half of the vector at every step. Here's a general recursive algorithm. If the problem can be solved directly for the current value of n, then we solve it. Else, we recursively apply the algorithm to one or more problems involving smaller values of n. And we combine the solutions to the smaller problems to get the solution to the original problem. Now, we'll see some examples of this that will help you understand exactly how this might work. Now, step 1 involves a test for what we call the base case. This is a value of n for which the problem can be solved easily. This step 3 is the recursive case, because it's here where we recursively apply the algorithm. Now, because the values of n for each recursive case is smaller than the original, each recursive case makes progress towards a base case. Now, whenever a split occurs, we revisit step 1 for each new problem to see whether it's a base case or a recursive case. Now, the steps to design a recursive algorithm. Here are the summary of characteristics. There must be at least one case, the base case, that's typically for a small value of n that can be solved directly. And the problem of a given size n can be reduced to one or more smaller versions of the same problem. Okay, that's the recursive case. So to design an algorithm, we need to recognize a base case and provide a solution to it, and then devise a strategy to split the problem into smaller versions of itself while making progress toward a base case, and then combine the solutions to the smaller problems to solve the larger problem. Let's see some examples. Here's a recursive algorithm for finding the length of a string. So if a string is empty, it has no characters, then the length is 0. This is our base case. So there's a simple solution to it. An empty string has length of 0. Otherwise, the length is going to be 1 plus the length of a string that excludes the first character. Okay, it's 1 plus, the recursive case now is taking the length of a string that's one length less than the original string. Here's some C++ code to do this. We have a function size. It takes a str parameter, which is the string, and returns the length of the string. Here's the base case where our empty string equals 0. Otherwise, we return 1 plus we recursively call size with a smaller string. This is the substring that eliminates the first character at index 0. Here's a recursive function to print the characters of a string. So we input a string parameter, and if we have an empty string, then we return. There's nothing to print. Otherwise, we output the first character, and then we recursively call print characters with the substring eliminating the first character. Here's a recursive function to print characters in reverse. It takes a string as input, and if we have an empty string, we do nothing. But notice the difference here. Now we first make a recursive call to print the characters in reverse of the shorter string that excludes the first character. And when we return from this function, in this case, once we've printed all those characters in reverse, then we can output the first character. And the idea here is that if all the other characters were output in reverse order here, then this puts the first character at the end, which will correctly finish the problem of printing this string in reverse. Now, inductive proofs work as follows. We prove a theorem is true for a base case, usually n equals 0 or n equals 1, and then we show that if the theorem is assumed to be true for n, it must also be true for n plus 1. Now, recursive proof is similar to induction. We verify a base case is recognized and solved correctly. Then we verify that each recursive case makes progress towards the base case, so that any new problems generated are smaller versions of the original problem. And we verify that if all the smaller problems are solved correctly, then the original problem is also solved correctly. Let's see how to trace a recursive function. So the process of returning from recursive calls and computing the partial results is called unwinding the recursion. So we start here with a call to size with the string ace of length 3. Since the string's not null, we will return 1 plus the size of the string CE. And this recursive call, size CE, represented by this blue arrow, will return the 1 plus a recursive call to the size of E. And the call to the size of E is going to be 1 plus calling size with the empty string. And this final invocation here will reach our base case. The empty string has a length of 0, so we will return 0 for this call to size. And thus we'll return 1 plus 0, which will give us a result of 1, and this arrow here represents 1 being returned as the result of this prior call size of E. And if the size of E is 1, we'll return 1 plus 1, which is a 2. So 2 will be the result of calling size on the string CE. 1 plus 2 is 3, so we'll finally have the result of our initial call of this string ace will be 3. So you'll notice that we keep making these recursive calls represented by the blue arrows until we reach the base case before there's any value returned from a function. So we'll finally return from this invocation of size and have to unwind the recursion until we eventually return a 3 as a result of our initial call. C++ maintains a stack on which it saves new information in the form of an activation frame. So an activation frame contains function arguments, local variables if there are any, and the return address of the instruction that called the function. In fact, the return address points to the very next instruction to execute once we return from the call to the caller. And whenever a new function is called, whether it's a recursive call or otherwise, C++ pushes a new activation frame onto the stack. This is called the runtime stack. So here's a figure that illustrates some activation frames. We'll start when we call size on ace, then the string ace is a parameter to the function, and we have the return address in the caller. And then when we make the recursive call, now CE will be placed on the runtime stack, and we'll have a return address back into the prior call to size, and so forth until we finally have the call to size of the empty string, and the empty string will be a parameter, and we'll save the return address back to the caller, which was size on the string of length 1. So once we've computed that the length of this string is a 0 and returned, then we'll pop that activation frame and we'll return back into the back to size, which was the call, the most recent call to size with the string E. And so we're using a runtime stack, and it's a stack just like sort of the LIFO data structure we talked about in chapter 5. A simple analogy for recursive calls is an office tower that has an employee at each level, each with the same list of instructions. And an employee on the bottom level carries out part of the instruction and then calls the employee on the next level up and is put on hold. And the employee at the next level completes part of the instructions and calls the employee at the next level up and is put on hold. And this process continues until finally the employee on the next level completes part of the instructions and calls the employee at the next level up and is put on hold. So this goes on and on until we reach the very top level. Now when the employee at the top level finishes the instructions, that employee returns an answer to the employee at the level just below. Then that employee who was on hold can now resume, and when they finish, they return the answer to the employee below, and so forth, until eventually the bottom is reached and all the instructions have been executed. So this illustrates the runtime stack and activation frames when we start with a call to the size of ace. It's not the empty string, so we'll make a recursive call for the size of CE, and so forth. And then finally, when we have the empty string, this reaches our base case, we'll return a 0. The result of the prior recursive call will be a result of 1. 1 plus 1 is 2. And finally, the result from our original call to size will be 3. And that brings us to the end of this slidecast.